Great. Okay, here is, now people ask, kids often ask questions about this because it looks like there's a feature that goes across here. Do you see this? Yeah. And there? This is actually a place, and the artist drew this in there actually, okay? This is a place where the galaxy was actually folded at one point and placed into a National Geographic issue. Okay, we go around every 200 million years. We go about 250 kilometers per second. Pretty sure that's faster than our 19 miles a second. So it's reckoned around a sun that is the source of all our power without doing a unit conversion, right? So our orbital speed due to our motion relative to the center of our own galaxy is much greater than our orbital speed around our own sun, right? And then of course we're rotating as an Earth, 900 miles an hour.
What do they think is in the center of the galaxy?
Ah, what is in the center? Either one of the following, either cheese, or most likely the reason why it's really bright like that is we think there's almost all galaxies have giant black holes, and black holes that are giving off light like that are called quasars. And of course black holes can't give off light, but they're accretion disks. The stuff circling them can give off lots of light, right? So stuff, again, as stuff heads toward a black hole, if it goes straight into the black hole, it goes in, right? But if you go it all off to the side, you start to orbit it, don't you? Right? And the closer you get to that black hole, the faster you spin, like those gates at IBII, right? And there can be a mighty powerful force pulling you to the middle. You just go fast, right? Okay, so black holes have these things called accretion disks, right? And if something comes in off disk, it hits the disk and gets on disk. Might change the orientation of the disk, right? So quasars are at the centers of all galaxies, pretty much. There are some quasars, right? And quasars are just these super bright things. They're just basically giving off the energy of that gravitational collapse. Question?
So, isn't it where they have some sort of electromagnetic field? And they have,
Oh yeah. There's exotic stuff with black holes. They have magnetic fields that make these jets. We think. Yeah. Bipolar jets. Yeah.
Assuming being into like time dilation and light speed of it and all that, and then also Zeno's paradox, can't you say that nothing ever enters a black hole?
Right.
You get closer and closer and closer.
In our frame of reference, but of course, in their frame of reference, and it goes, right? Kind of a thing.
Okay, so what happens if you go into a black hole? Do you die?
Well, Stephen Hawking, in his book, this is one of the best parts, right? He says, if you went into a small black hole, small black holes have incredible gravitational gradients, so it's going to pull you apart for your quarks, right? We think this would be the one thing that would separate quark from quark, possibly, right? So it would shred you up. He says. So Stephen Hawking says, what would be our experience if we were to fall into a black hole, or as we say in the academic circles, if one were to have a graduate student jump into a black hole, right? But larger. I don't know if he says that in the book, but maybe he said that in person, right? But the large black holes have very gradual things, and so those are the ones where you could actually surf in there and maybe, I don't know if you saw the movie Contact, or you can add your own graphic effects or something like that. It's a link to another universe, or who knows, right? But yeah, they basically warp space into themselves and could create like mini universes and things like this.
So it's like, that's like the Harry Potter test.
Yeah, it's a kind of a thing like that, yeah. Okay, here we are, where we are on our own spiral arm. This is zooming in. This is, of course, artists' renditions. But we're pretty accurate with this stuff close to us. We've got maps of it. Like this, when it says North America, they don't mean like North America. That's a galaxy or a nebula that looks like North America. Orion is here, right? Lagoon, these are all nebulas. Trifid, right? Cat's Eye. I'll show you some pictures of these guys. But anyway, where we are is actually a place where there aren't many stars around us. We're kind of in a place like, it's kind of like almost a drop of water or something, or maybe even a cataclysmic giant star might have exploded where we are now before our solar system was formed. This is a little bit crazy, isn't it? Right? That's what they think, is that there was a ginormous explosion probably that cleared out the space where we are. It's lucky that we're in such a space. There aren't many stars. There are plenty of stars side to side in the plane of the galaxy, but not many above us or below us, if we're talking about the galaxy going like this. Right? So this is a fortuitous thing. Right? Here's the Rosetta Stone galaxy, right?
Does that allow us to look out there?
Yes, it allows us to have an unimpeded look off plane in our galaxy, right? There's a lot to see. Okay. this is an elliptical galaxy. Okay, elliptical galaxies don't make very many new stars. Okay, they're like old people. They don't have children. Okay, stars that are made are just made by sort of like happenstance. Okay, and in fact, we believe that elliptical galaxies are the result of galaxies, spiral galaxies colliding with spiral galaxies. And the reason for this is if we look back in time, right? If we look back in time, there were more spiral galaxies then than there are now. There's far more elliptical galaxies now. Now, how can I say that? How can I say back in time there were more spirals, now there are more ellipticals? We can do this. This is a simple observation we can make. Yes, sir?
Because we can determine because of the speed of light that the things closer to us are more.
Yeah, we're seeing them more recently. Telescopes are time machines. If I look 5 billion light years from Earth, I'm looking at light not as it is now, but as it was 5 billion years ago, which is the universe is 13.7 billion years old, right? That's halfway to the beginning of time, right? Just about. So, yeah, we can do that. We can look at surveys. Distant galaxies, if you look at distant ones, there's more spirals. Near ones, there's more elliptical ones, right? Okay. Here's spiral galaxies. This is called the Whirlpool Galaxy. But think Whirlpool as in like washing machine, right? This is like a central agitator. It really is going faster in the middle, slower on the edge. That churning motion, just like one of those bread mixers, right, tends to mix stuff around. It grinds and mixes, and that causes clouds of dust and gas to collapse and become stars. Okay? So these guys, spiral galaxies, all create stars in an ongoing process. They all create 500,000 stars a year. Every year this thing, 500,000 stars, the next year 500,000 stars. Stars in these galaxies are all different ages. They're all different ages because it's making them in an ongoing process. Yes, sir?
What's the thing at the top of that picture?
Oh, this thing. That's a distant galaxy, probably an elliptical galaxy, right? And then what are these guys here? Stars that are much closer than that galaxy. These are foreground Milky Way stars. Okay. The other explanation for these guys is that they are actually supernovas in that galaxy. Now, how can you tell the difference? Well, here's how you tell the difference. Supernovas happen overnight. You look one night, this guy might not be there. The next night, it's there. Yeah? There we go. So that's the nova means new, right? Yeah, supernova, right? So there are people that do this. Supernovas are these really cool things that we'll talk about why they're cool when we talk about distance too, right? But there are people that go and they have their telescope look at like hundreds of galaxies every night, and there are people that have memorized all these foreground Milky Way stars, and they can tell you instantly by looking at it whether there's a new one there. Isn't that cool? That's cool. And they've got robots that try to do the same thing, but people are faster. It's one thing that computers can't do faster yet, is recognize shapes and things like that, right? Okay, here's a barred spiral. I promised you that I would show you. Can we stop, guys? I promised you I would show you a surefire way to identify barred spiral galaxies. Here's the bar of the spiral. Don't look so much here at the bar. Look more this way. Right there. Every time it always says barred before it says spiral. That's a barred spiral. Yeah, I bet you're wishing you had like a real astrophysics teacher now, don't you? There you go. Okay. This is our infrared camera. Infrared, as you recall, visible light bounces off of dust particles which are the size of visible light. Infrared has the ability to not be reflected by small particles. Okay, so you can see through. It's got a more penetrating radiation. Okay, as far as dust is concerned, these are a couple of galaxies that are colliding. It's not like two sperm battling out for like an egg or something like that, right? Okay. But anyway, this is a very cool thing. They've modeled this. These are two spiral galaxies. When they're done colliding, the result might be an elliptical galaxy. Okay. These two guys are colliding. They model this with supercomputers. There's people that sit there and model this using fluid mechanics, and they can get the same shapes that they see with the Hubble telescope. The one cool thing I'll say here is that whenever galaxies collide, or certainly if they even pass close to each other, okay, they get brighter. They get brighter because super new, short-lived giant stars are born, right? We think that's because getting close to each other disturbs them, churns them up. And when you churn up a galaxy, stars are born because clouds of gas that didn't